In this lecture, we're going to dig a little bit deeper into the original nonlinear models and see how do we produce linear models from them. And in fact, I have a wonderful quote here that says, classifying systems as linear and nonlinear is like classifying objects in the universe as bananas and non-bananas. What this means is that if you're walking around in the universe, let's say you're on Jupiter and you pick up something, chances are it ain't going to be a banana. Similarly, if you walk around and you pick up a system or a robot, chances are it ain't going to be linear. What that means is that linear systems are really, really rare. Yet, here I am 2 lectures ago bragging about how useful they are. So something's got to give here. And what it is that the nonlinear systems that are everywhere, they act very much linear, at least around operating points. So the linearization is a way of producing linear models from nonlinear models, or producing bananas from non-bananas, if you want. So what we're going to do in this lecture is produce linearizations, or linear models, from the nonlinear models that we start with. So here is a general nonlinear model of state space form. So x dot is now not ax plus bu. It's some general function f of x and u. And similarly, y is not a simple pleasant cx. It's some nonlinear function h of x. Okay, so now what we would like to do is we would like to find some kind of local description of what this system is doing. And this local description needs to be linear. And what I mean by local is that we have to pick an operating point. In the pendulum, we said, let's assume that the pendulum is hanging very close to straight down. So straight down is the operating point. And then what we do is we're going to have to define a new variable. So let's say that this is my operating point. This, in the pendulum case, would be the angle is 0 and I have no control input. Well, then my actual state is going to be the operating point plus some small deviation from the state. Similarly, my control input is going to be, well, the nominal operating input point plus a small deviation. And what we would like to do somehow is describe these small variations. And in fact, the new equations of motion that we care about, well, we're going to care about how delta x, this deviation from the operating point, behaves. Well, delta x is x minus x operating point, right? So delta x dot is x dot minus xo dot. Well, this thing is equal to 0 because it's a constant, right? So this is just 0. So here's my 0. So delta x dot is the same as x dot. Well, I know what x dot is. It's this. So now delta x dot becomes this. Okay, let's see if we somehow can simplify this. So this is my model. Now, luckily for me, there's something known as a Taylor expansion that allows me to write this on a simpler form. So this thing can be written as f evaluated at the operating point times this partial derivative of f with respect to x, also evaluated at the operating point. This is known as the Jacobian. And then you have the same partial derivative, but now with respect to u, evaluated at the operating points. And we multiply this with delta u here and delta x here. And then I have something that I call HOT, which stands for higher order terms. So this is where we're saying that the higher order terms, where when delta x and delta u become large, these matter, but for small delta x and delta u, they really don't matter. Well, why is this useful? Well, first of all, let's assume that we have picked operating points so that f of x naught u naught is 0, which means that we're holding the state steady. X dot is 0 at this point, which means that this thing goes away. Now, let's call these guys A and B. Why is that? Well, these are just matrices because I'm plugging in some constant value here. Similarly there, I'm plugging in a constant value. So these partial derivatives are just matrices. Well, let's call them A and B. And now let's do the same thing with y. Y was the output. We want to know what it looks like around this operating point. Well, we have the same thing here, plus this term, plus higher order terms. So let's assume that this thing is 0. So let's assume that we pick an operating point that kills the output at that operating point. So the output is 0 at that point. Well, then let's call this thing C. Right? Now I have A, B, and C. And in fact, let's summarize what we just did. If I have this nonlinear model, and I pick an operating point so that these two assumptions are satisfied, and then I look at small deviations from the operating point, then I can write delta x dot as a delta x plus b delta u, which is linear. And y is c delta x, where these a, b, and c matrices are given by these partial derivatives, also known as Jacobians. So this, ladies and gentlemen, is how you obtain linear models from nonlinear systems. Well, let's actually do some computations here just to know what's going on. So let's assume that x is in Rn, u is in Rm, y is in Rp, and we have f and h being given by these things, where really what we have is f1 of x is actually a function of x1 to xn of u1 to up, right? No, sorry, um, right? So when I just write f1, that's what I really mean. Okay, then df dx, this Jacobian that we talked about, the first one we need, well, it has this form. First component is the derivative of f1 with respect to x1. Then it's f1 with respect to x2, and so forth. And the reason why I'm writing this is not because I enjoy producing complicated PowerPoint slides. It's just we need to know what the different entries are. And it's important to do this right, because otherwise your dimensions don't line up when you produce your A, B, and C matrices. So that's df dx, or, as we now know it, A. This is my A matrix. Well, similarly, B is df du, right? And again, the first component is the f1 du1. This component is the f1 dum. Here we have the fn du1 all the way to the fn dum. So this is an n by m matrix, which is what we needed. And in fact, this is the B matrix then. So it has the right dimension. And not surprisingly, we do the same thing for our C matrix. And the reason, again, I wanted to show this is where the Jacobians come from. So if I write dh dx, this is what I mean. Good. Let's do some examples. So let's start with what's known as the inverted pendulum, which is slightly more complicated pendulum, where what I have is I have a moving base, my elbow in this case, and then I have a pendulum pointing straight up or with some angle. And by moving the base, the pendulum is going to swing, and in fact, it's going to fall if I don't do anything very clever. But the dynamics of this can be written like this, where theta double dot is g over L sine theta plus u cos theta. Okay, let's linearize this thing. The first thing we do is we pick our states. In this case, it's going to be theta and theta dot. And the reason I know that I have a two-dimensional system is I have two dots up here. So I have a two-dimensional system. x1 is theta and x2 is theta dot. Let's say that I'm measuring the angle. So y is x1. Well, then I get my f to be this 2 vector, and I get my h of x to be x1. Okay, fine. Let's pick the operating point where the pendulum is pointing straight up and I'm doing nothing. Right? And in that case, well, what is my A matrix? My A matrix becomes df1 dx1. So now I have to take the derivative of this thing here with respect to x1. There is no x1 there, so the first component is 0. Then I have to take the derivative of this thing with respect to x2, which is 1. So this component is 1. Similarly, I have to take the derivative of f2 with respect to x1. So now I have to take the derivative of this guy here with respect to x1. Well, the derivative of this with respect to x1 is g over L times sine. The derivative of that is going to be g over L times cosine x1. Well, the derivative of this with respect to x1 is actually going to be negative u sine x1. But I didn't actually write this here, even though I should have, arguably, because what I'm going to do is I'm going to evaluate this at the operating point. And you know what? U is 0, and in fact, x1 is 0, so this term actually goes away. So all I'm left with is this term, evaluated at 0, 0, and cosine 0 is 1. So after all these push-ups, I end up with g over L here as the non-zero term. Now, that's how you get the A matrix. Again, I would encourage you to go home, unless you're already home when you're watching this, and actually perform these computations so you know where they come from. Similarly, B, you have to do the same computation. In this case, you have no u up here, so you don't get a u in the first component. Here you have u cosine x1. Take the derivative of that with respect to u. We get cosine x1. We plug in the operating point 0, 0, and we're up with this elegant B vector here. C is particularly simple, right? Because h of x is x1, which means that C is simply 1, 0. So that was how we would go about getting these A, B, and C matrices. Okay, let's go to the unicycle, the differential drive robot that we've looked at, that we saw in the previous lecture that we had a little bit of an issue with. First of all, let's figure out the state. Let's say that x1 is x. Now I'm having a slight abuse of notation, right? Because x is also the full state. But this is the x component. x2 is y, and x3 is theta. And then let's say that we're actually measuring everything. So y is this. Okay. We can control the translational velocity, or the speed, and the angular velocity, right? So my inputs would be u1 is v, and u2 is omega. Okay. Let's compute now the linearization around x operating point is 0, u operating point is 0. Okay. If you do that, what you actually end up with, and I'm not going to show the different steps, you should do it yourself, is first of all an A matrix that's 0, a B matrix that looks like this, and a C matrix that's the identity matrix, which is not surprising since we're measuring both the XY position and the orientation of the robot. Now, this is a little bit weird, because if I write down the dynamics for x2, well, x2 dot, it's going to be given by the second row of everything. Well, first of all, it's 0, right, because my A matrix is 0. Then I get 0, 0 times u, so I get plus 0, 0, I mean, times u if you want. But this means that x2 dot is actually equal to 0. Well, x2 was the y direction. What this means is if I'm pointing my robot straight in the x direction, then apparently I cannot actually make the car drive in the y direction. That seems a little bit fishy, actually. What is going on here is that the linearization that we performed didn't quite capture all the nitty-gritty, exciting things that were going on with the nonlinear model. And this is an example where the nonlinearities are so severe that the linearization, as applied directly, doesn't entirely apply, because we lost control over the y direction, even though if I have a car, I can clearly turn it. I can drive it and turn it and drive in the y direction. So here's an example where the linearization actually doesn't give us just what we wanted. And the punchline here is that sometimes the linearizations give reasonable models, with inverted pendulum, for instance. And sometimes they do not, with the unicycle. And with the unicycle, we have to be a little bit more careful. But the fact that I want to point out, though, is that when they work, when the linearizations work, they are remarkably useful. Even though we're finding them around operating points, they seem to work better than what we really theoretically have reason to believe, which is why we do a lot of analysis of the linearizations rather than the nonlinear models, and then take what we learned from the linearizations and apply it to the nonlinear models. Thank you.